Hi, everyone. It's a pleasure to be here, and thanks a lot for giving me the opportunity. My talk today is going to focus exactly on this question, the question of the reflection and transmission of energy across interfaces. And I'm going to try and convince you that holography is a great tool for answering questions of this sort. Right, I understood that the audience is a little bit mixed, so I'll try and I have like some what is holography short slides, and the problem itself and the results should be possible to understand without prior knowledge of gravitational setups. So I hope that that's going to be okay. And you should feel free to ask me questions at any time. I don't need to get to the very end of my talk, so I'm happy to stop and discuss. All right, so the talk is going to be based on these three papers and one work in progress about how to answer. So the two first papers deal with two-dimensional setups, and the work in progress is about higher dimensions, and I'll get to that towards the end. And that's going to be the outline. So I'm going to start with a little bit of introduction about conformal interfaces. I will then present the problem of energy transport in conformal interfaces, and I will explain what is special about it in 2 dimensions. I will then have a very brief introduction to what gravitational holography is and how it can try and help us answer this question when the theory is strongly coupled. I will present 2 setups of interfaces in holography, a thin brane setup and a smooth interface. And then I will tell you the answers for the reflection and transmission experiment in these 2 setups, both in 2 dimensions and some preliminary results in higher dimensions. And summary and outlook as usual. All right, so let's start with a brief overview of conformal interfaces. And I'll leave the outline so you can keep track of where I am. So conformal interfaces. So before conformal interfaces, what do I refer to as interfaces? Interfaces are extended objects that split a system into 2 parts. I know it's used sometimes to say something else, but that's what I will mean. So for example, for example, if I'm talking about a system which is 1 + 1 dimensional, 1 space, 1 time, then these are impurities in a chain. So I could have a chain and something in the middle splitting the chain in 2, which is there for any time. In, say, 3 + 1 dimension, these will be some sort of walls splitting the system into 2. When I talk about conformal interfaces, what I mean is something more. I mean interfaces between 2 critical systems that preserve a very large or the largest possible amount of the conformal symmetry. So conformal. So of course, since the wall is there or the impurity is there, that can't be the full conformal symmetry, but it can be a very large part. So in d greater than 2, that's an SOD comma 1 from the SOD, comma 2 symmetry of the entire, sorry, D plus 1, comma 1 of the entire system. And in D equals 2, so 1 plus 1, that's one copy of Virasoro. All right, so what are conformal interfaces good for? Where do we encounter them? So they appear in many places in physics. Let's see. I think that's the, is that the maximal span? It goes down. Oh, let's. Ah, great. Thank you. Sorry. Right. Sorry about that. Right. So this is a bit of motivation where we find those in nature or in general. So we find conformal interfaces in many places in condensed matter physics, including junctions of quantum wires, line and surface defects in the 2D and 3D criticalizing models. We find them in holography, which is a duality between quantum conformal field theory and gravitational systems, where we see them as dynamical branes in ADS where gravity can be localized, and we see them in supergravity solutions such as Janus. We find them in the context of quantum information when discussing quantities such as the boundary entropy or the interface-related entanglement entropy. They are rather useful in recent discussions of islands in black hole evaporation also. And they appear in monotonicity theorems along RG flows. Where certain anomaly coefficients are proven to be monotonic, and many, many more. So they can be found in really many places. So how do we describe them? Let me tell a little bit. The way we describe them is the following. So imagine that, so now I'm going to add back my time direction. And imagine that the interface is located at some value of x, say x equals 0, and has some coordinates within it, including time, which we will call, say, yi. Now, from the point of view of symmetries, the interface can't really preserve all the symmetries that we used to have in the space without the interface. So, for example, the obvious thing is that doesn't preserve translations in the direction of the interface. And that means that energy conservation, which follows from that, is altered, meaning that if we talk about the stress tensor of the theory, that stress tensor will be conserved in all directions that don't involve the interface, but it will be modified, so not conserved, in the direction that involves the interface. And we'll have some delta function contribution of an operator living on the interface called the displacement. Oh, sorry. All right. And so from these modified conservation laws, we see that while the stress tensor is not conserved in the whole space, there are some gluing conditions for it, like consistency conditions for it on the two sides of the interface, which is that txt has to be continuous, on the two sides. Let me say, so that was like how to describing conformal interfaces. All right. Yeah, many things change a little bit from what we're used to. For instance, primary operators can get expectation values and so on. And there are many good reviews about that that one can read. But I won't explain more at this point. What happens in 2 dimensions? So in 2 dimensions, we have a much larger symmetry group. Typically, when we have a left and a right CFT, so here again with the time direction pointing up, have some CFT living on the left and some CFT living on the right. Imagine the interface being located at, say, x equals to 0, or the on a given time slice, the impurity located at a certain point. This setup can have much more symmetry than the higher dimensional setups. In that, the maximal symmetry is that it preserves one copy of the Virasoro. So preserves the one that doesn't displace the interface. And again, there are gluing conditions for the stress tensor that can be expressed in terms of its holomorphic part and anti-holomorphic part. That's just the continuity of this TXT component. Sorry. Of the stress tensor. All right. Let me see. Some interesting properties about conformal interfaces in 2 dimensions is that certain correlation functions of the stress tensor are completely fixed. The 2 and 3 point functions of the stress tensor are fixed on the 2 sides of the interface. So the 2 point function looks like that. For the left stress tensor, a similar expression for the right stress tensor, where this C is the left or right central charge. And there is a new guy here now in 2 dimensions, which is the expectation value of the one left and one right stress tensor. There is a new coefficient involved, which I'll call C left right. Oh, sorry. Right. The 3 point function is fixed. I won't write it as well, but the 4 point function is not. Yeah, what did I do? I corrected, yeah, to the 4th power. Sorry, that was a typo. Oh, yeah, sorry. So either left or right, either left or right, either left or right against central charge, and that's to the power of 4. Yeah, sorry, I don't know how to gauge if this is too simple or too, it's okay. If the left and right part are preserved separately, meaning that they don't talk to each other, yeah, I think I would call that topological, yes, yes. Because you see, I mean, in a sense, you factorize the theory in exactly 2 sectors, and like kind of this new component that is there, if they don't talk to each other, it's not there. So you would, yeah. He was asking if, yeah, me too. But he.
Second line equals 0. Not the first line. I mean, the first line is a property of.
But he was asking if the gluing is separately for the left one and the right one. Does it necessarily implies that they don't? Yeah. Then TL separately and. Right. Topological, I would say, if they don't talk at all, in the sense that if this correlation function is vanishing, I would say it's topological.
Second line equals the first line, then it's topological. So there'd be no scattering.
So sorry, but your question was about if the left is 0 in itself and the right is 0 in itself, or if just the holomorphic part is talking to itself and the anti-holomorphic part is talking to it. Just the holomorphic and just the no. Then not necessarily, right? Because I mean you do have some some relation between the two, and you could have a correlation function. I mean they know about each other, so. Then not necessarily. I mean, you'll see the role of this guy, and this guy is telling you, yeah. I mean, in a sense, he's telling you if the theory is topological. Yes, sorry. Right, exactly. So that would be the factorized case. So if that separately is 0 and that separately is 0, that would be boundary. Yeah, but two boundary CFTs that don't talk to each other. Sorry.
Presence of the interface, T-left bar becomes.
Yeah, that's true. So I didn't write all two-point functions. You're right. That's something that already can happen. I mean, you probably used, right, that in a CFT you don't have things like that, T bar, T left, T bar left, right? But already when you have a boundary, you do have these type of correlation functions. The reason they usually don't exist is you don't have a distance to build from the Z and Z bar coordinates, but now you do because you have the distance from the interface. That's a distance that can participate. So they would go like, I don't know. In the case of a boundary CFT, I guess would be something of this kind, but now you'd have I don't remember the precise coefficients, but you'd have an influence of this C left right coefficient. It would participate in these distance from the boundary correlations. No, so okay. The thing I'm going to so I will tell you when I talk about 2D specifically, I will tell you about results that were derived not by us in the CFT, talking about in the context of this energy experiment about universality of this reflection and transmission. And what I will in practice do will be to compute this coefficient C left right from an equivalent holographic experiment. In some type of interfaces. So I won't be, the things I'm reviewing now are not our work. It's just the setup and things that are known from the CFT point of view. And then in a specific example, I will explain how to compute them using holography. Say why it's hard, why do you need, yes, sorry.
Given CR, is there any constraint on the value of CLR? For example, maybe it cannot be too larger than.
Yes, absolutely. So there are constraints. It's that CLR has to be between 0 and the minimal of C left and C right. But I will talk about that. I mean, it will make a lot of sense in a second. In a second, it will like be completely obvious why that's true. So. Okay, wait. So I'm going to erase and write it again in a second. All right. Okay, very good. So that's 2D. That's, let's say, higher D. Very constraining. Okay, so that was just some generics of conformal interfaces. And now I want to talk about this energy reflection and energy transport experiment. That's the point number 2, which is the question I'm interested in. So energy transport from conformal interfaces. Right, so imagine that I have a conformal interfaces between 2 CFTs. Can you see here? No, right? Yes? Here, yes? Here. No, it's okay. All right, so imagine a scattering experiment at which you send some energy or some incoming excitation in a direction. So that will be CFT left, CFT right. That's a constant time slice and the wall, say, between the 2 theories. And now I perform the following experiment. So I send an incident lump of energy made out of, ooh, you're taking a lot of risk here. So you're sending an incoming lump of energy made out of whatever things you want, any primary operators, descendants, packed in any shape you want, and send it in the direction of the interface. A part of it will reflect back, and a part of it will keep moving and will be transmitted. And that's the experiment that or the question that I want to answer is, what is the portion of energy which is transmitted, and what's the portion of energy that is reflected? That's a rather simple question. Right, so I define 2 coefficients, which are going to be how much energy is transmitted and how much energy is reflected. Since the CFTs don't have to be identical, the answer doesn't have to be symmetric when we have a perturbation incoming from the right or from the left. So I will append small labels to tell you whether the experiment started with an incoming perturbation from the left or from the right. All right, so before I move on, and tell you what is known about those transmissions and reflection in interface CFT, let me mention that scattering experiments in CFT are very subtle because of the lack of asymptotic states. So one really has to think very carefully about what does it mean to have a certain amount of energy at infinity in a CFT where distances don't matter, so what really is infinity and so on. There are papers trying to formulate that. So essentially, the answers I will give you are based on their definition of what is the incident energy, what is the, and these are like Hoffman-Maldacena, the conformal collider physics. And I mean, there are several people discussing that carefully. So let's say this is in CFT without an interface. I don't know, maybe I just write. And with interface, there is Maineri, Penadones, and Rousse. But anyway, so I write scattering definition in CFT can be subtle. But since other people studied or defined it in some way for us, I won't say much more than that. Yeah, no, the problem is usually you want to refer to asymptotic states when you define a scattering experiment. So usually you want to look very, very far from the place particles scatter. And in CFT, that's kind of a subtle concept because there's no notion of distances. It's a scale invariant. So there is some subtlety in exactly how to define those quantities. But I will just say that people have thought about that in the CFT context. They define them using Einek operators on the null infinity of Minkowski space. So there are definitions, but yeah, I won't get into too many. I'm happy to talk more.
Is there any reason that we what energy not infinity are determined by the
well, I guess, yeah, depends how you need to be careful in what you define. But I mean, if what you mean by momentum has to do with txt, then I guess probably the fact that it's continuous around the interface.
Everything moves at the speed of light.
In a CFT2. Well, I don't know, half the speed of light is, I guess. Sorry? I mean, yeah, I think the fact, you know, in CFT2, since you have the holomorphic and anti-holomorphic part that are separately conserved, you know, if I build waves, this will be e to the ik z, x minus t or x plus t. So this necessarily means they move at the speed of light. I'm not sure, is it obvious in higher D? I don't know. Yeah, but proportional, you know, again. Yeah, but but isn't the speed of light the constant? Okay, maybe.
What you're saying. If you know how the energy is reflecting.
Yeah, okay. Yeah, sounds good. All right. But you mean in any dimension or in 2D? Yeah, we can, sorry, yeah. Yeah, we can. I mean, we should talk about that later. But I think it's not obvious if you add an additional direction to the stress tensor, and you know, okay, if you turn off this additional direction and you are and you stay with effectively a 2D problem, then you again have this, and you write conservation equations and so on, you will again get this holomorphic, anti-holomorphic part. Maybe it's true in general. Yeah, I don't know. Okay. Yeah, we should. Okay, I will say some. We can, yeah. Yeah, but that doesn't mean, you know, you can't have in any direction modes. Yeah, but I'm happy. Yeah, you. Okay, we can. Yeah, we can talk. All right. So, yes.
But can we say more confidently what the in and out states would be for these waves?
Yes, you can absolutely. So okay, in the context of the, you can do it in the context of the interfaces. For example, you'll find the answer on how to build these states. Typically, you take, say, a primary operator, and you integrate it against some function to bound it inside the region where the size of the region is much smaller than the distance to the interface. And and in this way, yeah. So again, that's yeah. Maybe I should let me. Yeah. To make it, that everything well defined, you need to localize it within some packet. But you will see that, okay, specifically in 2D where this was defined in the CFT properly, you'll see that it doesn't really matter the shape. Okay, so very good. So what do we know about these coefficients? So in general dimensions from CFT point of view, not so much. In 2 dimensions, we know quite a bit. So let me tell you what we know in 2 dimensions. All right. All right, so energy transport from 2D interfaces. Yeah, so here's what's known from the CFT point of view. That's due to papers, an earlier one from 2007 by Kuela and Runkel and Watts. And a later one from 2019 by Maineri, Penedones, and Rousset. And essentially, the point is that it's very crucial that we're in 2 dimensions, because 2 dimension has much more symmetry. And so what is found is that this enlarged symmetry has a very interesting consequence, which is that the scattering experiment is completely universal. And that means, so I don't mean that across theories it always gives the same, but for a given theory, independent of whatever lump of energy you send in the direction of the interface, the amount of scattered energy and the amount of reflected energy is independent of this incoming state. So independent of incoming state, which is, I mean, it's a surprising consequence to some extent. Because it's much more general than just saying, it doesn't depend on a length scale. It really doesn't depend on whatever content appears in the wave packet. And it's given, so let's say if I'm doing a scattering experiment from the left, the transmission will be C left right over C left. And if I do an experiment sending an incoming wave from the right, it will be C left right over C right. So you see that if we turn off the C left right, there will not be any transmissions, and the 2 CFT will get decoupled. To have these 2 things, and of course reflection is always one minus transmission, so that's maybe not very surprising. That's energy conservation. So you see that to have these things, so either of them between 0 and 1, from either side, that necessarily implies that this C left right coefficient, which was in the 2-point function of the stress tensor on the 2 sides, has to be between 0 and the minimum of C left, C right. So that's your, plugging this back in then tells you that the transmission, let's say from the left or from the right, doesn't matter, has to be between 0. 0 transmission is full reflection, and the minimum of 1 and C left over, C right over C left which has a nice interpretation if we think of C left and C right as the number of degrees of freedom. What this means is that it's impossible to have perfect transmission, coefficient 1, from a theory with less degrees of freedom to a theory with more degrees of, from a theory with more degrees of freedom to a theory with less degrees of freedom. That would then necessarily be less than 1, because there are kind of not enough degrees of freedom to carry the perturbation away. So that has kind of an intuitive explanation. Yeah, there are more recent works tying these coefficients of energy transmission or bounding with them, coefficients related to entanglement transmission. And again, I won't talk too much about that, but there also works on that. All right, that's the end of part 2. So any questions? Yeah.
And usually I would think, like, so you said in the end that intuition would, if you transport things from the side with more degree of freedom to less degree of freedom, the scattering cannot be perfect.
Its transmission cannot be perfect, so something has to scatter back. Because if you don't have enough degrees of freedom, it cannot carry everything away into the next, the second CFT. No, it's not an average. It's the answer for any state that you, any state. That's the universality. As long as there are some caveats. I mean, as long as there are no spin to quasi-primaries except the tensor and so on. I mean, there are caveats, but
suppose I have a uniform CFT stacking with another one with conformal boundary, so the other layer is just n there. That's anyway, I would think the mode in the first layer, because the first layer is a uniform CFT, everything should be perfect. So you have perfect transmission for some of the modes. It's not the case by Holography.
So it can happen. You can definitely have perfect transmission when you have two identical CFTs, because then, yeah. So when the right and left are the same central charge, so this, in a sense, the same number of degrees of freedom.
Homogeneous CFT stacking with another one. I thought the C left will add up.
But another one which is identical to the first? Yeah, then that's okay, right? Because then that's the right central charge and the left central charge, they would be the same. So that would be 1. So the minimum of 1 and 1 is 1, and you're good to go. I mean, you can go all the way to 1. The problem is if you have you're trying to transmit from one with a higher central charge to a lower central charge, then you cannot do it.
As long as you only load up the main packet and the free scalar that's at the boundary, right? So you ought to be able to get transmission equals 1 in either direction. Is that your idea?
Yeah.
Okay. So what about that example?
I think the problem there is that you have a second spin 2 current, right? So that's
Yeah,
that's
right.
the caveat that you were mentioning, right? You have the second quasi-primary spin 2 in the second where you stack.
Right. But probably, I don't know if they...
Very good one.
Thanks. I guess free is very special anyway. Yeah, I mean, you can have decoupled funny sectors with a stress tensor to each one of them that usually you don't have when you start coupling things. You will have just one stress tensor and that's it.
Plus maybe black holes also, like the photon radiation.
Wait, but this would be, so this is all like flat on flat space. Yeah, maybe if you attempt, and what I will tell you is how to translate this to some gravitational problem, but the gravitational problem won't be the transmission and reflection of some quantum state of something riding on the curved background. But yeah, definitely, that's interesting. I don't know the answer. Yes.
Reflection of energy, but what about some other symmetry, some other charge? Do you
Yeah, there are similar results. There are similar coefficients. Usually, you would have to add currents. Yeah, that's one more level of complication. You can find some things about that in the yeah, and also about transmission of relation to transmission of entropy in scattering processes. You can find some things in Couch's recent paper from 24. They're nice things.
Say what cases with CFTs are long-range Ising, let's say 2D, one side, something without an energy momentum tensor. Are there? And you can still define, but you still have a Hamiltonian, but probably you can't if you don't have an energy momentum tensor. I guess you can't define these quotation functions. Are there some?
Yeah, I don't know. Sorry, I don't know.
Maybe you have this surface inside of a larger bulk, like a 2 + 1 dimensional bulk, this surface that you drove through that you ask transmission questions, I guess, on this surface. Maybe it's orthogonal to what?
Yes, so now I'm trying to understand. You mean, but scattering from what? So if you
This is in some higher dimension, like maybe this is a defect in some higher dimensional theory, so maybe it doesn't have a stress tensor, maybe it's a long-range Ising model or something like that. Are there ways to define these reflection and transmission? And you still have like a Hamiltonian.
Yeah, I'm not sure. I mean, I'm happy to. I don't. Yeah, I don't know. All right. Right. So that's the end of point number 2, because in higher dimensions, there's not. I mean, I don't know of this type of results in CFT for general CFTs. I mean, yes. Yes.
The impurities completely characterized by scattering matrix.
Yes. Yes.
Here there's no scattering.
Right. So if you go in this like older paper of Queller-Runkel, the way they got, they defined this result by looking for something that would be somehow the equivalent of a scattering matrix. It's again all these subtleties about defining experiments in CFT, but they looked at a quantity that had nice properties that kind of looked like a scattering matrix, and that's how they guessed the result for the transmission reflection, which was only like proven more formally later on.
You don't mind the gap theory in CFT? Well, free Fermi, yes.
With the defect, you define a scattering matrix. The defect is completely defined by the matrix.
At the fixed point. I mean, yeah, CFT. Well, free Fermi and massless free Fermi.
Massless free Fermi.
Okay.
This matrix and everywhere. At least when you compute gap, maybe it's what you mentioned is something. Here is you want gap. Yeah. Anyway.
I know you.
No, that's perfectly fine. And I can. I mean, it's self-consistent without that part. So I think that's fine.
Definitely when you change from one CFT to another, you have to change something continuously, right? Is there some width of the interface, or you're thinking about the delta, the theta function that changes from one to the other?
I mean, I don't think of every quantity as being a delta function localized. It's just that there is the location of the interface, and the symmetries refer to this location. But if I have a profile, for example, of a field, you could have some. Yeah.
Something that changes from one CFT.
Yeah. I mean, right. Yeah.
So there could be.
Right.
And anytime a smooth function that introduces scale, you're assuming a scale invariance. So with the symmetries, you'd assume this thing has to be infinitely.
But that's not. It's not obvious, right? I mean, you can have.
But you can create a scale for the interface, not for the CFTs.
Eventually, you look from far away, cross-grading them.
Yeah, but it would disappear.
you could have a position dependent. So instead of a mass term, usually would break the conformal symmetry. But you could have, mass over distance from the interface to some power, which is exactly the right one to cancel the dimension of the mass. And I think that would have that could have the right symmetries. So maybe, yeah, I don't know. Yeah, maybe non-local like potential. Right. Very right. Okay. Okay, very good. So that's 1 and 2. And I will say a few words about gravitational holography. So just to say, the question I'm trying to answer is, I would like to compute these coefficients, or C left right, or these coefficients, in a strongly coupled theory with many degrees of freedom, which is a hard problem in general. And that's where gravitational holography is going to become useful. So what's gravitational holography? So gravitational holography is a duality or a correspondence between two seemingly different physical systems. Duality between quantum field theory and gravity. For those of you unfamiliar with it, let me just remark how special it is, right, to have two completely different physical systems that have nothing to do with each other, that are described by the same equations. And the CFT is often, right, just a second, sorry. So the point is that there exists a dictionary between problems in quantum field theory and problems in gravity, which allows translating problems that may be very difficult on one side to problems that are sometimes manageable on the other side. So it's a tool. And what I will do today is I will use it to translate the quantum field theory problem of scattering in interface CFTs to a manageable gravitational problem. It works also the other way around. People have used it to take very hard problems, such as the black hole information paradox, and try and translate it to more manageable problems in quantum field theory. So it's rather useful. The best understood example of it is and it doesn't work for every QFT and every gravity setup, just for specific ones. The best understood example is the ADS CFT correspondence. In which the two sides of the duality are a conformal field theory in d dimensions without gravity, and on the gravity side, a d+1 dimensional untitled space, which is a solution to Einstein equations with a negative cosmological constant. Right, and the CFT is often depicted as living on the boundary of anti-de Sitter space. Right, there are many very good reviews written on it, but I'm just using it as a tool to try and answer the question about the reflection and transmission coefficient, because it maps to a more manageable gravitational problem, for example, in higher dimensions. All right, so that was gravitational holography in a nutshell. Now, what about conformal interfaces? In holography. It turns out that there are many examples of conformal interfaces that can be implemented in holography. The two models I will focus on today, well, I don't know, maybe I will skip the second one, but the The first one involves a gravity setup where a thin brane is embedded. And the second one are a class of smooth geometries often used in the context of supergravity. They include Janus interfaces and so on. And I'm going to use this to translate the scattering experiment to a more manageable gravitational problem. So let me just say why. Let's see. Yes, the interface is on the CFT side, and it maps in the bulk to some modification of the usual setup where you just have this hyperbolic, essentially anti-de Sitter space solution. So that's some solution of Einstein equations with a negative cosmological constant, and you have to somehow, and that's dual to just a CFT without an interface. To make it dual to an interface CFT, you have to add something in the gravitational setup, and that could be either a dilaton, which takes a profile, or some thin brane. So maybe with so just to say why am I going to use this very bombastic tool to address a simple problem of scattering? And the point is that ICFT scattering at strong coupling is hard. How to solve, and that gives us analytic control of it in specific examples. And the other side is that these specific models are of interest in developing holography for itself. For instance, the thin brane models have played a rather important role in the recent studies of the black hole information paradox on the gravity side. So important to understand the models. The holographic models themselves. Yes. Not that I know of. Do you know?
No.
No, I think.
Never popped.
Yes, absolutely, exactly, right. So. Yeah, that's part of the. You would, because it's again, it's not universality between different theories. It's within a given theory to different incoming states. But yeah, even the ability to calculate the coefficient in a specific theory is, yeah, is interesting. Yes.
I think the expectation is that CLR would be replaced by the two-point function of the displacement operator. At least that's what that would be what we expected. We had some computation, but we never published.
And do you expect universality? Any type of universality?
There were some stronger conditions than into the, I think, but some kind of universality. Yes, I need to look at that.
We will see. I don't know. Then we have to see if they. Yeah, we should talk. Yes.
You defined is between two CFT which can be different.
Right.
Then SFT on the gravity side will be also different.
Absolutely. That's a great question because I'm going to answer it in a second. Yes. Sorry. Right. So the point is that you can, okay, in the thin brane, well, in both cases, but specifically in the thin brane, you can take a gravitational solution which is ADS with a certain cosmological constant, and glue it with ADS with another cosmological constant through a thin brane. And with the dilaton, you can also have it. Yeah, absolutely. No, you can get generality to some level. It's of course not completely general because it needs to have a gravity dual, which makes it not completely general. But I will say now. So let me see. No, you can definitely not find a gravity dual for any CFT interface that you have in mind. I mean, certainly, not even if it's conformal. I mean, they have very special properties. They are infinitely strong coupled, and they have many degrees of freedom, right? At least, you know, we are working with semi-classical gravitational solutions. So they are valid for describing very specific CFTs in very specific limits. But I think already quite interesting because they can be strongly coupled and very non-trivial. All right, so let's talk a little bit about the first one of these two, the thin brane model. The thin brane model, so what it does is, as you anticipated, it glues two anti-de Sitter spaces of generally different radii. So it solves Einstein equations for an action of this form. So let me explain what that means. So that's Einstein-Hilbert action with a negative cosmological constant expressed in terms of this L left, which is the radius of the solution. It's a hyperboloid basically. That's an Einstein-Hilbert action with a right, so another radius. And that's a constant tension brane that connects the two. So the picture you should have in mind really is these are asymptotically ADS space. So these are ADS spaces. So some ADS d+1 of the left and ADS d+1 on the right, which are spaces with negative curvature. And that one has a boundary, which is the CFT on the right. This one has a boundary, which is the CFT on the left. What did I do? Okay, I don't know. And they are glued together with a finite energy density brane of tension T. That's the Ricci scalar, the Newton's constant, the different coordinates on the left and right radii of the characterizing the different ADS radii, the tension, and the induced metric on the brane. Because this one would be integrated in the full space, and it's just like the dimension of the wall. Yeah, exactly. So you remember I said that ADS is kind of living on the boundary. So on the boundary, I will have a CFT left and a CFT right glued along. Yeah, it lives on the boundary. I mean, it's tilted. I will explain why in a second. But you should think that's where the interface lives, and that's kind of the gravity dual, always adding one more dimension to every object, more or less.
By theory, you mean also it's a probe brain, it doesn't back react, or
It does back. It definitely does back react, but in a way that is solvable, under control. Yeah. So what it does, turns out, is that it just, instead of, if you had a tensionless brain and the same CFT, it could be like half ADS and half ADS kind of. So it would go. Yeah, the angle would be.
No, I'm not thinking of tension. I'm thinking of probe brain. So a probe brain could have a tension, but just doesn't modify the geometry of.
No, so it modifies the, yeah, exactly. So that's what I'm saying. So
Right, but the junction condition is usually if the brain can react.
it opens an angle. That's the back reaction. I mean, you can change coordinate to see that it really modified the half geometry that was part of it. Yeah, what the junction conditions do is that it really opens up an extra angle, and so you have a little bit more than half ADS here and a little bit more than half ADS on the other side. So that's the back reaction.
So it's a minimum. Well, it's a thing that it's under control.
To some
My
extent.
experience that, okay, well, maybe we'll talk later about higher dimension. Usually in higher dimension, this is much more severe.
Absolutely, yeah. It's a mess in higher dimension. I will tell you something about higher dimension. Not everything there is to know, because it's in progress. But I think I'm gonna skip the smooth brains, and whoever wants to ask me about that later, I'm happy to talk about that. I think that will be a smart choice given the time. Yes. Sorry. Right. Oh, you mean at the corner or something like that? Yeah, there are. I mean, I don't know if we are like 100% careful in the treatment of the corner, because at the end of the day, the answer we're interested in are, yeah, we assume the gravity solution doesn't diverge at the corner, which may be, it's a good question if it's a justified assumption, but that's the assumption we took. Yeah. So you have a stress tensor that doesn't blow up at the interface. Yeah, no, no, it's not smooth. So in principle, if you think about it as the delta localized energy and you just write Einstein equation, what they would integrate to would be Einstein equation with a certain cosmological constant here, Einstein equation with a certain cosmological constant here, and gluing condition across the brain that I will write now, which will have a jump at the level of the first derivative.
Space with different radius. Are you saying you cut the geodesic of the two sides and then try to glue them? What's the angle?
Yes, I will write. Yes, I will write. It's along the geometry of the brain is ADS2, and you can pick the angle. So ADS, no, not ADS2, ADSD. The ADSD plus 1 has a slicing of different brains, which are. Sorry, this is ADSD plus 1, and that has the geometry of ADSD, every constant slice. So depending on what angle you take, you can change the induced metric on the brain. You can change what's the effective radius of this ADSD slice, and you can bring them to match across the interface, depending on the tension. So, yeah. Right.
So the intersection, interface between two hyperbolic space, is that right?
Yes, that's, you mean in the, not in the CFT side. I'm just translating in the bulk.
Yes.
That's an interface between two hyperbolic geometries with the different radii. I mean, we take a hyperboloid, you cut it in two in some place, and you just glue it to another part. I mean, not exactly cut in the same way from another hyperboloid, and you glue them together with some constant energy density transition between the two. So. Well, it's a surface, so a geodesic it can't be, right? I mean, a geodesic would be a dimension 1 typically, right? It would be the trajectory of a particle. But even then, oh, you mean within a given time slice, is it a geodesic? Maybe we can check it. I mean, we can check. Yeah. No. I think it's very easy to check. I just don't. All right. Okay. So the equations of motion we said have solutions like that. So let me just write. So on the left, there's a metric that looks like that. ds squared, either left or right, is L either left or right over z squared minus d t squared plus d z squared plus dx squared of left or right, every coordinate. And the two patches are glued together by Israel matching condition, which is just essentially Einstein equation in a pillbox around this delta function localized energy, which are that the induced metric on the brane should be continuous, and the extrinsic curvature should jump by a fixed amount fixed by the tension. And the induced metric. So these are the gluing conditions that one has to solve between the two patches to find where the brane is, and that can be done, and it leads to the following conclusion. So if I define the angles from the tangent, so I have half of ADS space plus some angle theta left, and half of ADS space plus some angle theta right, then these angles are fixed by the tension, fixing, let's say, the brane location. Like that. So L left over cosine theta left is L right over cosine theta right, is d minus 1 tangent theta left plus tangent theta right over t, the tension. What did I do with the tension? I did something funny. No, yes, no, that's fine. All right, so that fixes the angles completely if we know the tension and these L left, L right. How should you think about these L left and right from the point of view of CFT? The L left essentially fixes the central charge on the left. So it's not an equality, but in 2D it's a proportionality, and either way there is a relation. L left fixes the central charge on the left. And L right on the right. And the tension fixes the properties of the brane. So for example, of the interface, sorry. For example, the interface entropy. So if we look at entanglement entropy of an interval centered around the brane, that quantity will contain a modification compared to the case without an interface, which often we call the boundary entropy or interface entropy. And that will be like this log G into the, and that will be fixed by the tension. So all these three parameters have an interpretation from the point of view of the CFT. So now when we express the outcome of the scattering experiment in terms of these three parameters, essentially what we're doing is to express it in terms of the central charge of the left and right CFT and in terms of the properties of the interface, for example, the boundary entropy. Great. Yes. But I can't. It's a bit of a misleading picture because I would like to draw the ADS in a way which is loyal to the usual coordinate system I use to describe ADS, in which case that's a little bit more than half ADS, and that's a little bit more than half ADS. So, you know, when I glue them together, I get a kinky angle, but I don't have like this kink in from the CFT perspective. It's just flat, but I cannot put all these properties together on the blackboard. Sorry, why don't I have theta left plus theta right equals pi? That's inconsistent with the gluing conditions. So the gluing conditions, when the tension is non-vanishing, forces you. That's the back reaction. You always have? As long as I have a tension. Yeah, that's the vanishing. The straight one is the vanishing tension limit, right? Mm-hmm. Right, exactly. Right. Yes. Yes, you can. That would be right. Yeah, that would be the limit in which the two radii are equal and the tension is vanishing. In which case, essentially, you have no brane. Right. But from this point of view, if they are topological, the scattering experiment should be trivial, right? Because it cannot know, you know. So it has to be fully transmittive. So from the perspective of transmitting energy, I think it's maybe less interesting when it's topological. Yes, right. CL, all these coefficients are related to 2D. You have central charges in higher dimensions as well, but yeah, I think that's not exactly the description. I mean, the stress tensor two-point function has a much more complicated structure, or three-point function has a much more complicated structure than it does in 2D. Yeah, so wait. I have an answer. Sorry, I'm a slow thinker. The answer is that in general, there is not a relation. But in the specific theory that I'm studying now, since there is just one parameter, which is the tension at the moment, there will be a relation. But more generally, they are independent. Yeah, no, that's not a general thing. It's just about these thin brane setups. But more generally, you should think of T as fixing. Well, if it's a thin brane, then it's a very special case. But in general, it's a parameter that characterizes the new property of the interface. Yeah, sorry, I'm trying to. Okay, just to say that there are bounds on the tension. It can't be anything you want. So the tension is, there's some coefficient here that depends on the dimension, but let's say in 2D it's 1, and it comes from a constrained point at which the brain kind of hits the boundary and the geometry changes to become de Sitter. There are different reasons for the lower and upper bound, but just to say that the tension can't just be anything in the world, it has to be within these bounds to be consistent. Yes, absolutely. You can. It's more subtle. Yeah, I mean, this would have come. Yeah, I guess it would come naturally when you talk about the smooth. Yeah, I mean, you mean. It is, so this brain is on an ADS-D slice. That's the default setting. Okay, when you start perturbing it, it will be a fluctuating thing, but around an equilibrium, which is an ADS-D slice. Good. We can also, I mean, not we, but some people can construct solutions with the multiple thin brains, and okay, interesting things about that. I'm going to skip the smooth brain, and now I will tell you what we find for the reflection and transmission. But one second, let me think. I probably need to skip a little bit more than that. Yeah. Okay, so I will just say in words. What you have to do to implement the, okay, let's right here. The scattering, so that's that was 4. We did 3 and 4. Let's talk about reflection and transmission in holography. So essentially what you have to do now is you have to slightly modify this setup and put an incoming perturbation. We are doing that linearly in the size of the perturbation, so we are assuming the perturbation is small. In 2D, it doesn't matter too much because we know the scattering should be universal. So as long as we got the right coefficients, we're good to go. In higher D, would potentially matter. Right. So what exactly is the scattering experiment in holography? What we have to do now is turn on a certain perturbation, and the way we did that, because our setup contains only a metric, is to turn on a certain expectation value for the stress tensor. So we're going to have an expectation value for the stress tensor, which should take a form of some shape. This shape, working with linearized gravity, with small perturbation, not completely linearized gravity, but the perturbation is small. Any stress tensor can be decomposed in terms of plane waves, and then, okay, just Fourier decomposed. And since we are doing everything with small perturbations, so linearized, we can treat each one of the modes separately. So for example, in 2D, let's say Fourier decompose in plane waves, or at least that's what we would want to do. Okay, let me start with 2D. Sorry, it's becoming a mess. And then what we would want to do is essentially solve the gravitational setup, which has this stress tensor on the boundary, which means solve Einstein equation with a boundary condition that yields this stress tensor. So let's talk about 2D for a second. So in 2D, that means that we would want a stress tensor of the following form: the alpha beta left, dx alpha left, dx beta left is epsilon, just to say that the perturbation is rather small. 1, the incident energy, e to the I omega t left minus x left. That's the incoming perturbation at the speed of light. D t left minus x left squared plus e to the I omega t left plus x left. So that's the incoming perturbation, and on the other side, we only have an outgoing perturbation, which looks like, sorry, yeah, right. The x alpha, the x beta. Tau, no, reflection, no, yeah, transmission, sorry, that's the transmission. That's on one side. On the left, I have the incoming and the transmitted wave, and the reflected wave, sorry. And on the other side, I have the transmitted wave, e to the I omega t right minus x right. And I will tell you in a second. So in higher dimension, it's a bit more subtle. But anyway, I would like to turn off or to decompose my stress tensor in terms of plane waves and essentially solve the gravitational setup with modified boundary conditions in such a way that now the metric is modified in such a way that when I expand it around the location of the boundary, so in terms of the coordinate z, which is the distance from the boundary, at the dth order, I get the stress tensor. So it has an expansion where that is in any number of dimensions. That is not. I will say in a second that you cannot do in any number of dimensions, but you would want at least asymptotically to get waves. I mean, you would want to be able to, you could decompose any stress tensor asymptotically in terms of waves. Doesn't mean that you would have waves in the whole of space-time. So essentially in higher dimensions, what happens is that the profiles are not really waves, but asymptotically you can superpose them to make waves. And from these waves you can, Fourier decompose whatever packet that you want. Right. You mean that you could have computed it, just compute the two-point function of the stress tensor. Right, that would be equivalent, absolutely. Well, the two-point function, I guess, in a sense, it's a reaction to a fluctuation in itself. So yes, but I think it's a... So you will see a simplified version of that in the cancellation of the dependence on the frequency, which then means that it doesn't matter. All these waves will all reflect with the same coefficient, and so it doesn't matter what you build. This will all reflect with the same coefficient. But of course, you would want to add matter fields. It's not as easy as it seems. Absolutely. I think that's a very interesting problem. I think we gave it a shot. People don't know that much about, well, even the natural boundary conditions that you would want to impose on a scalar with a thin brane. If I add a scalar to the geometry, it's just very hard to solve. Many things are very hard to solve in practice, but okay, very hard doesn't mean impossible. I think there's many interesting things there. Okay, but wait, I'm approaching the end of my time. What am I going to do? Okay, I'll just tell you what you do. So the scattering experiment is you would like to build a stress tensor, whatever wave packet. I'm going to work with small perturbations. So this wave packet I will decompose in Fourier modes and treat every Fourier mode separately. And then what I do is I try to solve the metric in such a way that it has the right asymptotics to reproduce this stress tensor on the boundary of the theory. And if you do that, you're going to get the following answer for the, I mean, these coefficients will be forced to have some values. So essentially, do this perturbation to the metric and then solve for the gluing of the brain. The brain changes shape. It starts fluctuating. And if you solve everything, plus you impose no outgoing condition, no outgoing waves on the brain, which is a standard condition in holography for correlators. For example, yeah, it's like retarded correlators have these like no outgoing wave. Okay, sorry. Then you will get the following answer. Let's talk about, so in 2D, following answer. So, solve a metric and brain shape from Israel matching and no outgoing wave condition. Waves on brain. And you will find the following. So in 2D, the transmission from the left or the right is 2 over L left or right, 1 over L left plus 1 over L right plus the tension to the -1. Yes, the tension, exactly. So sometimes it's expressed with this parameter. And in this case, you see 8 pi g sigma. That's, yeah, that guy has dimension of 1 over length. Because that has dimension of length to the d minus 1. And okay.
The holographic computation of CLR.
Absolutely. That's effectively the holographic computation of CLR in this model, of course. I mean, and this is just 2D. Wait, I will tell you then. Okay, that's just 2D. Just to say a few. So consistency conditions. You can check that when you turn off the tension and the 2 central charges are equal, the transmission is 1. Everything passes. You can check that when you put in the. I wrote earlier there are constraints on the tension between something and something. So if you input them, you will find that T left right is exactly bounded by this. So everything seems to match quite well. And sorry. I think it's it has to say something about the fact that it's a retarded correlator-related experiment or something like that. Sorry, that you get right. That you get more strict in higher dimensions. You get a stricter bound explicitly bigger than 0. If you add 1 more brain, then you can relax that and go all the way to 0. Right, higher dimensions, few words, then I will finish. So in higher D, it's really much more complicated for many reasons. One of them is that if I have a higher dimensional interface plus time, then now the scattering can also have angles with, like it can arrive at an angle with respect to the interface, because now the interface has a spatial dimension. So that makes it more rich. And of course, to help a difficulty, there is much less symmetry. So that's a very complicated thing. But you can still try and address it from holography. The obvious place to start is to look at waves that are hitting head-on. That's already much more complicated, because it turns out that the solutions for the stress tensor, which are allowed by the holographic setup, are not plane waves. They are Bessel functions. And Bessel functions have the property that they oscillate, but they decay at infinity, all of them. And so originally, we were very puzzled by how can you even build plane waves or anything that doesn't decay at infinity from these Bessel functions. And it turns out that you can. So you can build some very rigorous mathematical theorems that explain how to sum series of Bessel functions in such a way that they do reconstruct at infinity plane waves. And then you can do this at least head-on scattering experiment, which is the very simple thing. And when you do that, what you will get is this. So worked quite hard for this one extra coefficient. Over 4, it seems. Expressed in terms of the central charges, it has a different form because the central charges in 2D go with the radius squared. It does seem to satisfy, this is very recent now, so it's very preliminary. Yeah, in terms of the central charge, it has a form which is looks quite different because in 3, that's in ADS 3, sorry. This is in ADS 4 dual CFT 3. Must depend on the dimension, but we don't know yet. So this is for head-on, light-like excitations. That already required quite a piece of machinery already on top of what is in lower dimensions. Right. Yeah, and yeah. In higher dimensions, the central charges go like L squared. So if you re-express it in terms of central charges and boundary entropy, would look a little bit different. But seems consistent with the bound and seems consistent with turning off the interface and so on. But OK, so that's work in progress. There are many open questions. So open questions. Which are, I would say, what happens when we study more general perturbation, when we have a small angle, for example, in the incident energy. So angular dependence. There is the obvious question of what CFT results one can obtain in general without using holography. And finally, there is relating this to critical systems, like condensed matter style critical systems and true experiments, so cond-mat relation. So there are many more things to study in the context of this scattering experiment, but I hope I convinced you that it's an interesting one to do and that holography can help us study it. And yeah, that's it. Sorry for taking 5. It's not impossible. I think it's possible. I think it's interesting. There are so many interesting things in this. Yeah, I mean, adding fields, adding a black hole even in 3D. I think so. That would be a CFT setup at finite temperature, and you would have like some. So without the perturbations, the setup of having a black hole with a brane has been solved in a paper by Kostas Bakas and his student. So you can find that. With perturbation, I don't think it has been addressed. I don't know. I think that's very interesting. So, and I think you have what to expect, at least in 2-dimensional boundary, 3-dimensional bulk. You know what to expect because there are results for finite temperature on the CFT side. So anyway, yeah. We can add more fields. Yeah, I don't know how for the scattering experiment from high, yeah. Yeah, you could. I mean, right, you would have like particles scattering, yeah, as well. Not in, yeah, well, not in 2D. You can't have it in 2D, right? In 2D, that's the, you put a point, it's already an interface. But in 3D, you could.
In that case, you have just a CFT and you have a horizon. Doing a fluctuation of the metric when you're shooting it with the momentum field, you're like shooting it at the horizon and you get some universality. That fluctuation. To me, this kind of feels like just taking that, rotating that 90 degrees. It's not exactly, it's not a horizon in the same sense, but.
No, I agree. I think.
It might be similar. could even imagine if you trace out one of those ADSs, the ADS would have a mixed state.
Another thing that is very interesting, I mean, if we are already rotating, another interesting thing is if you rotate that to be at a constant x, to be at a constant time slice, which would be a quench. Like you would be moving from a certain CFT state, putting something in and quenching it to become another CFT. And you could ask questions about what happens. This produces some things that start moving from the quench. So there is also if we are talking about interesting questions involving rotating the setup, that's, I think, also an interesting one. Yeah. Okay, yeah, that was, sorry for the time planning. Yeah, sorry, yes.
In IoT, so again, for the metric, when you solve the Israel condition, the metric in the bulk stays ADS. It doesn't change. Because I have experience in the boundary with an end of the world brain. Well, you solve the Israel condition in this case with nothing on the right hand side, and you find that the back reaction is very complicated. But I had also black hole, so maybe it was more involved. So what you find is that you have the same setup that as in just an angle? Or
No. You have to change the metric, absolutely. Okay. No, you're right. Sorry, I didn't say. You can do it. Okay. Just you have to work a bit hard, okay. But you can do it. No, you can find the solution because it's linearized in the perturbation. It's not really linearized it's not linearized in the holographic direction, of course, if we're turning off waves crawling up the brain. But if you do for a small perturbation and you keep track of the leading order in the perturbation, you can, you can solve for the metric, but it will tell you that the stress tensor cannot be built from you don't have modes that are plane waves everywhere, for example.
Yeah, but even before asking about the plane wave, I'm just asking about the setup without. So suppose I want to look for a holographic dual of an interface in IRD.
Yes.
So was this already done? Or?
Oh yeah, but that would be a brain in connecting to ADS patches.
Without any with ADS
with ADS
with the metric in the bulk being ADS. If I look at a single point in the bulk, I don't realize that it's not ADS.
Yes.
Okay.
Yes. Okay. But once you have a stress tensor perturbation or something, then no. Yes. Yes.
As you go through the family of conformal interfaces on CFT, how does that correspond to the family of brains in the gravity type? Do you get different degrees of freedom with brains?
So when you change the properties of the conformal interface in the bulk, I mean, within the class of this specific model would be changing tension, which would change the gluing angles and everything. But you have richer models, so you can have multiple brains, and you can have even completely smooth solutions with a dilaton profile that I didn't get the chance. But yeah, it's a rich landscape of possibilities. I think it's making the interface kind of more rigid. So what you see here, so if you look at that, you see that when I have a larger tension, the transmission becomes smaller. So it's kind of a resistance of the interface to transmitting energy. That would be one way to understand it.
Oh, I understand. But like if the CFT has the CFT interface might have many parameters specified, but the relationship to the tension would be quite complicated, I guess, right? So if you tell me the CFT interface, like as a matrix, as mentioned, say as a matrix on the limit operators, computing the tension from that, is that like the tension corresponding to this choice into the conformal space?
I think the scattering matrix or whatever scattering-like matrix observable is related to this experiment. But for example, the entropy added by an interval which includes the interface compared to an interval that doesn't include the interface, which is kind of the equivalent of the boundary entropy, that can be computed. That has been computed, and you can find it in the literature. Yeah, absolutely, absolutely. Yeah, so the smooth Janus were an attempt to go away from this very toyish localized lump of energy that is completely bottom up and okay, but
Top-down models.
sometimes closer to it.
Just to build on that, this is a very simple model where there's only one parameter describing the interface, which is the tension. So pretty much anything you calculate that interface, it'll be the tension times some dimensionless T times G or something.
Is it
Right.
one-to-one?
But again, you can split the different parameters by considering more elaborate models. For example, yeah, two brains. Yeah, there are not many interesting questions there too. Okay, anyway, good.